So in this video, I'm really just going to show you the quickest way to calculate the sample Pearson correlation coefficient. And I know right now I have the population Pearson correlation coefficient formula up here, but what ends up happening is the population and the sample formula end up being the same thing when you do a little bit of math. You can transform them into each other because the n's or the n minus 1s end up canceling each other out. And I'm also going to show you the one formula, but we're going to use a different formula than this one. But this one's kind of more conceptual and the other one's more practical. That's why I show you both. So this is the formula for the population Pearson correlation coefficient. And we're going to use rho. And rho is this p looking thing. So the correlation between x and y is rho. And that's for the population. And then on top we have the covariance of x and y. And it ends up being the variance of x and y. And I'll show you why I call it that. And it's how much x and y move together. And then on the bottom we have the product of the two standard deviations. So we multiply the population standard deviations together. So here's a formula for covariance. And you can see the top looks a little bit familiar if we kind of transform it a little bit. So the top is the variance between x and y. Now, if you think from before, we normally have x here and x here. So we would have this, you remember you get the deviations and then you square them. And when you square them, you're just multiplying them together. So if we take this off and put this here, look, we have the variance formula. So this would be variance of x. But now we want the covariance. So the covariance is the variance of two variables. So it's how much they move together. So that's just a conceptual thing. And here is the sample Pearson correlation coefficient. And again, we have basically the same formula, but with sample data. And so R is going to be the number for the Pearson correlation coefficient instead of rho. And then we have the covariance of x and y on the top, and then the standard deviations at the bottom, the product of them. But instead of the population standard deviations, we have the sample standard deviations. And here's the sample covariance formula, and it looks the same. The only difference is the n minus 1 at the bottom because we have to deal with degrees of freedom. So this looks very similar to the variance formula, the sample variance formula, but it's the variance between x and y instead of just one variable. So here is the formula that we're really going to work with though. The other one was more conceptual one. So at the top we have the covariance, how much they move together. And at the bottom we have the standard deviations. Okay? And we kind of dealt with them before. We talked about variance and we talked about standard deviations before and how that relates to the mean. Here we have a different form of variability or spread. So you should know what the sum of squares are of x and y. And remember we used that in the variance formula. So remember variance equals the sum of squares x divided by n minus 1 if we're doing the sample variance. So we're just taking that top part and the up here is really the covariance. So the covariance equals the sum of the products divided by n minus 1. And so what happens is this and this cancel out, and we're left with the sum of the products divided by the sum of the squares for each of them. Okay? And you do it for x and y and multiply them together. So this is the formula we're using, but it's same as the other formula. So the top is how much they're moving together, and the bottom is how much they move separately, and that standardizes the number. Okay? And if we do it this way, then it's a little bit quicker. And this formula is based on the total variability, and the other formula from before with the covariance and the standard deviation is based on kind of average variability. But in the end, they all equal the same thing. So here we have the sum of the products, and that's equal to the deviations for x times the deviation for y, and then you add them all together. Here we're going to go over the steps to calculating the Pearson correlation coefficient. So the first step is to find the means of both variables. So we have x bar and y bar. Step 2 is to find the deviations for each value for both variables. So we subtract the mean for each value of x, and we subtract the mean for y from each value of y. Step 3 is to multiply these deviations together to find the product of the deviations. Step 4 is to add the product of deviations to find the sum of the products, which is called SP. And then step 5 is for each variable, square the deviations. So we're going to square the deviations for each x variable and square the deviations for each y variable. And then step 6 is to add the squares up for each variable and find sum squares for each variable. So you have two sum of squares. We're going to have the sum of squares of x and sum of squares y. Then finally, step 7 is to fill in the formula. So we're going to have the sample correlation R equals the sum of the products divided by the square root of the sum of squares x times the sum of squares y. Now I'm going to go over an example of how to get the Pearson correlation. And we're going to do it for the sample data. So we have an N of 5, we have 5 people, and we have their height and weight. So person 1 has a height of 65 and a weight of 112. Person 2 has a height of 71 and a weight of 136, and so on. You can see this data. So this data is paired by person. So remember, the first step is to find the means for both variables. So we're going to have a height mean. So I'm going to use h for height instead of x, and you can use any letter you want. I'm using h because it's more informative to me. So we have a mean height of 68 inches, and we have a mean weight of 137.4. So you can stop the video and find that for yourself if you want to double check. Then our second step is to find the deviations for both variables by subtracting the respective mean from each value. So first we're going to do the height deviations. You can do it either way, but that's just how the table's set up. So I'm going to do 65 minus 68, and that equals -3. So I subtracted 68 from this value because that is its respective mean for the height. So it's going to be -3. Then I'm going to do 71 minus 68, which is 3. And then I'm going to do the next one. So it's going to be 69 minus 68, and that's 1. And then do it again. And again for the last person. And if you add these all up, it's going to equal 0. And you can double check that, but we don't really need to know that information. Remember, the same thing with variance. The deviations are going to equal 0, so that's why you square them in variance. But we're going to do it a little differently here. Now I'm going to do the same thing for weight. And so I have 112 minus 137.4 because that's the mean for weight, and this is a weight value. So I'm going to have negative 25.4 here. Then I'm going to do it for person 2. Now I have 136 minus 137.4. So I'm going to have negative 1.4. And do it for the third person, the fourth person, and the fifth person. And again, these will equal 0, and you can double check it, but we don't need to know that information. Now we're going to do the third step. We're going to find the products of the deviations by multiplying the deviations across the rows. So we're going to find the deviation for the first person, which is -3, and multiply the deviation for that same person for the weight, which is -25.4. So we're multiplying the deviations for the same person. So we're going to have -3 times -25.4, and we get 76.2. Then we're going to do it for person 2. We have 3 times -1.4, which equals -4.2. And then we're going to do it for the third person. 1 times 15.6. 0 times 4.6 for the fourth person, you get 0. And negative 1 times 6.6 for the fifth person. And here, we do want to add these up. So step 4 is to add all the products of the deviations to get the sum of the products. So this is the top part of the correlation formula, and this part is going to determine if it's positive or negative. So if you add these up, we get 81. So here we have a positive correlation, right? If your height increases, so should your weight. On average, it tends to. This is a pattern of these 5 people. Seems to be that if your height increases, so does your weight. Or it tends to. Now, the fifth step is to square the deviations for each variable. So like we do for variance, but we're going to do it for each person. So we have the deviation for the first person for their height is -3, and we're going to square that to get 9. Then we do it for the second person for their height deviation. We get 9 again. We do it for the third person and we get 1. 1 squared. 0 squared is 0. And -1 squared is 1. And now we're going to do it for the weight. So we have -25.4 for the first person for their weight deviation, and we square that to get 645.16. We put that there in our table. And then we do it for the second person, and they had a -1.4 weight deviation, and we square that to get 1.96. Then we do it for the third person, we get 24.3 to 243.36. Then we do it for the fourth person and get 21.16, and for the last person we get 43.56. That leads us to the sixth step, which is to add up the square deviations for each variable to find the sum of squares for each variable. So the sum of squares for the height is 9 plus 9 plus 1 plus 0 plus 1, and that equals 20. And then the sum of squares for the weight is all those numbers in the last column there added up to get 955.2. Then finally, you want to use the formula. So we have the sum of products and the sum of squares for x and y, or for height and weight, and we're going to fill it in. So we have 81 divided by 20 times 955.2. And you want to remember your order of operations. So we're going to multiply first. And that gives us 19,104 at the bottom, and then we're going to take the square root of that. And that gives us 138.22 at the bottom. Now we have 81 divided by 138.22, and that gives us 0.59. And that's between -1 and 1, which it should be. So if you don't get any answer that's between -1 and 1, then you did something wrong. So we have a positive, pretty strong correlation between weight and height in our sample data.